Greetings and welcome to lecture number 4 of our series on basic circuit theory. I am Razavi. Today we will talk about circuit theorems, in particular Kirchhoff's laws, Kirchhoff's current law and Kirchhoff's voltage law. You might have seen these before in physics, and they may have called them Kirchhoff's node law or node equation or node rule and Kirchhoff's branch laws or something like that. But here we call them Kirchhoff's current law or KCL for short, and Kirchhoff's voltage law or KVL for short. But before we go there, let's take a look at what we covered last time in lecture number 3. We saw that we had a few more devices to talk about. So we talked about the dependent current source, and we said that it's just a current source whose value depends on some other parameter somewhere else. It could be a voltage or a current, and this current source acts as a current source. It wants to push its own current into the circuit, but it imitates another quantity somewhere else. Then we talked about resistors and Ohms law, and we saw that it's a simple linear relationship between the current and the voltage, and that relationship can be cast as V equals Ri, and that gives us a straight line through the origin with a slope of R. Or we can write I in terms of V over R, and that gives us a different characteristic. Either of these is fine, and we call these the IV characteristics of a resistor. All right, then we also talked about the concept of equivalent resistance, and we said that if we have a black box with only 2 wires coming out of it, we can try to find the equivalent resistance between these 2 wires. And to do so, we apply a voltage source here, call it Vx, and we measure the resulting current, Ix, and Vx over Ix, in analogy with Ohm's law, will give us the equivalent resistance that we see here. So that's a very useful method that we will be looking at later in the context of Thevenin equivalent and Norton equivalent. One last point related to the definition or identification of devices in series or in parallel. 2 devices are in series if they share one node only and they carry the same current. So whatever flows through R1 has to flow through R2. There should not be any branching out here. And then 2 devices are in parallel if they share both of their terminals as shown here. Once they share the terminals, they automatically have equal voltages anyway, so we don't have to say that they have to share 2 terminals and they have to have equal voltages. All right, so with these, now we can go ahead and look at Kirchhoff's laws. Kirchhoff's laws are very powerful, and these laws, along with everything else that we have learned so far, allow us to analyze any circuit that's given to us. So that's why we want to go through these carefully. Okay, so let's start with KCL, which is a little more intuitive. So Kirchhoff's current law. And it's pretty simple. It says that if we have a node in the circuit at which a bunch of branches converge, so we could have, for example, resistors here or capacitors and whatnot, and these all branch at this node. Kirchhoff says that if we add up all of the currents that are entering this node, the result should be 0. So if I have this current entering, by entering I mean this arrow is pointing into the node, and similarly this current is entering, so we call this I2. If my pen works, I2, etc. So we say sigma I sub j is equal to 0. This summation is on all of the branches that are terminated or connected to that node. We have to remember that this summation is true only if all of the currents are entering or all of the currents are leaving or exiting the node. Then we can say that's true. And it makes sense. Why? Well, if you think of a water analogy, if all of the water molecules that are arriving here have to go somewhere. So some of these currents have to be positive, some of them have to be negative. Here we rely on charge conservation. We mean that if charge is entering from these two branches here, it has to go somewhere, it cannot disappear, so it has to come out of this node. So some of these currents have to be positive, some negative, so that they add up to 0, simply because charge cannot disappear. So Kirchhoff's current law is really a result of charge conservation in any circuit. So it's relatively intuitive, and we can apply it to any circuit that we have. Now, in some cases, we rewrite this equation in a slightly different form. And we might write it like this. So this is also equivalent, and whichever you're comfortable with or the occasion calls for, you can try. So we can say sigma I sub j, j is equal to sigma I sub j, j. What does this mean? It means that I'm going to add up all of the currents that are entering. So we're going to write entering. And that sum has to be equal to all the currents that are exiting. So we write here exiting or leaving. Okay? So that's another way of writing it. Rather than bring this to this side and say the sum is 0, we can just look at it that way. So for example, if I go back here and I say, well, I am denoting my currents like this. So this one is going this way, this one going this way, so call that I2 and I1. So I said these two currents are entering the node. They're bringing charge into the node. Now that charge has to go somewhere, so it's going to end up going this way, for example, right? So if you call this I3, I4, and I5, then I can say I1 plus I2, meaning the currents that are entering is equal to I3 plus I4 plus I5. Okay? So sometimes this is more intuitive to write. So depending on the situation that we have, we might try this or we might try that. Okay, so that's KCL, and we will be using this extensively in all of our circuits. Let's see if there's anything here that I can say. Let's look at a little example. So here's an example of applying KCL. So suppose I have a current source which I have called I2, and then I have a resistor and a battery. So here's a resistor R1, here's a battery V1, and these are all connected like so, and we are interested in this current here, IX. So how much is IX? Okay. All right, so we eyeball the circuit for a moment, and we see that we have a node here at which we can apply KCL. So for example, we can say the sum of all the currents entering the node has to be 0, or we can say the sum of all the currents entering should be equal to the sum of all the currents exiting. But before we try to write KCL, let's just look at the circuit and see if we can make some predictions. Can we predict the current through R1, this current going this way? Well, yes, because the voltage across R1 is actually this battery. This battery applies this voltage between these two lines everywhere, right? So if this voltage is V1, this current is given by V1 over R1. Okay. So now, as far as this node is concerned, I have this quantity, I'm looking for that quantity. So what I can write is, for example, IX is entering the node plus I2. I2 is also entering the node because it's oriented this way, right? I2 is going this way. These two have to add up whatever is exiting, and this current is leaving the node. So I can say this is equal to V1 over R1. So the quantity of interest Ix is just equal to V1 over R1 minus I2. Okay, it's very simple. So it's just a quick example of how we apply KCL. All right, let's look at another example which relates to what we discussed last time. So last time I showed you the series combination of two resistors, and I calculated the equivalent resistance based on our technique of applying Vx and measuring Ix. Now I have two parallel resistors, and I would like to know how much the equivalent value is. So R1, R2. Okay, someone puts in a black box and says, find the equivalent resistance of this black box between these two wires. So we apply our usual technique. We say, okay, we got Vx and we measure Ix. Or we can apply a current source, Ix, and measure Vx. It's the same thing. All right, so what can I say here? Well, how much is the current through R1? We know that because this is a voltage source of value Vx, and that voltage source applies its voltage between these two lines wherever we go. So this voltage is also Vx, which means this current is Vx over R1. And similarly, this current is Vx over R2. So now I have a current coming in called Ix. I have two currents going out called these values. So the entering current has to be equal to the exiting currents. So we have Ix is equal to Vx over R1 plus Vx over R2. And if I find Vx over Ix, which is the resistance of interest, it would be like this. Vx over Ix is equal to 1 over R1 plus 1 over R2. And if we just cross multiply these, we're going to get is equal to R1 R2 over R1 plus R2. All right, so two resistors in parallel are equivalent to one of value R1 R2 over R1 plus R2. So that's easy to remember. You might have seen this in physics that you would say the inverse of the equivalent resistance is equal to 1 over R1 plus 1 over R2, because that would be the inverse of this. But this is actually simpler, so often for only two parallel resistors, we write the result like this, and then it's easy. So that would be our equivalent resistance for only two parallel wires, right? Let's see if my pen responds here. That's the parallel resistance. Okay, so that's another application of KCL. This equation is extremely useful because in many circuits we can identify that two resistors are in parallel, so they can readily reduce to a single resistor using this equation. All right, moving on. A couple of observations about this result that are useful. So, observations. Do you agree that this equivalent resistance is always less than R1 or R2? So the equivalent resistance, which is R1, R2 over R1 plus R2, is always less than R1 or R2. Why is that? Well, consider this situation, right? If you just cross out R1, you end up with R2 over R1 plus R2, which is always less than 1. So this is always less than these two. So anytime we put two resistors in parallel, the result will be less than the original resistors. And that's something that we have to remember. Sometimes it's a good thing, sometimes it's a bad thing. Okay, the next observation to make is if R1, for example, goes to 0, so we have two resistors in parallel and one of them becomes smaller and smaller. What happens? The net result also goes towards 0. As you can see that they are multiplied here. So that means that the parallel combination also goes towards 0. All right? In other words, the smaller resistor dominates the situation. Okay? And what if one of the resistors goes towards infinity? So, for example, R1 goes to infinity. If R1 goes to infinity, we end up with only R2. And that makes sense, right? Because if R1 goes to infinity, it's an open circuit, it's gone, and all is left is R2. So we say R equivalent, the equivalent resistance that we have here is equal to R2. So these are little properties of the parallel combination that are very useful for our future studies. Okay, moving on to the following. So let's talk about Kircchoff's voltage law. So that would be KVL. So let's see if this pen, let's see if I can try the other pen. So KVL. So Kircchoff's voltage law. All right, Kircchoff's voltage law says that if we take a circuit that has a bunch of branches and we make a complete round trip, so to speak, along these branches, the sum of the voltages along these branches should be 0. So let me explain what that means. So suppose we have a circuit and has various branches consisting of many different devices, right? You have inductors, capacitors, whatever, right? And of course, there could be many other things connected here. All right? But we identify a loop here, and a loop consists of a bunch of these branches. And wherever we start from, the definition of the loop is that we come back to that point. So if I start from here and I travel along this resistor, this capacitor, this inductor, this resistor, and this resistor, I come back to the same point. So around a loop, the sum of the voltages has to be 0. So for example, if I call this voltage V1, and I call this V2, and I call this V3, and so on, then I can say that sigma of a Vj over J equals 0 around a loop. So the concept of the loop is critical here. We have to come back to where we started. If we stop somewhere in the middle, the result is not correct. So I cannot say that V1 plus V2 plus V3 is 0, because we haven't gotten back to the original point yet, right? We have to write this voltage and this voltage and this voltage, add them up all to find the result and set that result to 0. So that is the definition of, that's the result of KVL. Now it turns out that KVL actually relates to conservation of energy. What it says is that, remember how we define voltage? We said the voltage between 2 points is the amount of energy necessary to take a unit charge from one point to the next point. So all it's saying is that if I start from here, for example, and I travel this way, I take some charge up here, some charge up here, some charge up here, but eventually the charge comes back to the same point. So the charge has not changed its energy, net energy, as it goes around and comes back. And because of that, the sum of all these voltages has to be 0. But it's okay if you don't appreciate that, that's all right. We just want to remember this rule. Now, this rule can be a little confusing. Why? Well, here's the situation. Let's continue to write these voltages. So it's V3, then I have V4, and then I have V5, and then I have V6. Okay? All right. Now, I am trying to write my equation. So I'm going to say, okay, let's add up all of the voltages that we have. So we write V1, Then do I write plus V1 or minus V1? And then I write V2. Do I write plus V2 or minus V2? Then I write V3. Do I write plus V3 or minus V3, etc., right? How do I figure out if this should be plus or minus? All right, so two different approaches, of course, with the same result. One approach is to say, if I go down the potential, I will write a negative sign. So down the potential means what? Means if I go from high potential to low potential, I'm going to add a negative sign for this V1. So that's one approach. Then I would say I am going down to potential minus V1. I'm going down to potential minus V2. And in fact, the way I have marked these pluses and minuses, you can see that they will all be negative, right? Going down, going down, going down, going down. So this will be all the way to minus V6 equals 0. So let me cross this out and write this is approach 1. Approach 1. Okay, so you can do that. And for example, if I have another circuit here, so let's just say I have a resistor and whatnot and something like this, and I just come along and randomly assign my voltages. So I say, okay, this is V1, this is V2, this is V3, and this is V4. Here's the loop, right? I start from here, go along these branches, and come back to the same point. I would like to write KVL here. No problem. So we're going to start from anywhere we want, doesn't matter. So let's say start from here. And I'm saying I'm going from high potential to low potential. So that would be minus V1. I'm going from low potential to high potential. That would be plus V2. I'm going from high potential to low potential, minus V3. And I'm going from low potential to high potential, that's plus V4, equals 0. All right? So we can stay with this notation, right? Yeah, at any time we go from high potential to low potential, that voltage will receive a negative sign. Anytime we go from low potential to high potential, that voltage receives a positive sign. And that's how we got these signs here. Another approach is completely opposite. So approach 2 would be where we start out. So approach 2. If we go from negative, or I should say a better way of saying it is to visualize it is to say the following. So we say, if we see if this pen works. Okay, let's see. So if we see a negative sign, okay, so if we are at a point and we see a negative sign, then we assign a negative voltage. And then assign a negative voltage. And vice versa. Okay. So let's try that for example, this circuit and this circuit and see how it goes. All right. So I'm going to change the color of my pen here to red. Okay. So these are exactly opposite of each other, and the reason I go through both of them is that in some previous courses like physics, you might have seen this technique rather than this technique, or this technique rather than this technique. So you really have to be comfortable with both of them. You pick one and you stay with it for the rest of your life, but you still have to remember that there are two ways of doing this. Okay, so let's go with this and write the equations for this circuit here. All right, anywhere we want, we can start. So let's start, for example, here. So I am going this way, and I see a positive sign. So according to this prescription, if I see a positive sign, my voltage will be positive. So I'm going to write plus V1. Then I travel here, and I see a positive sign again. So I say plus V2. And it just turns out that for all of these, they're all the same. Reach a plus, reach a plus, reach a plus, and so on. So this will all plus V6 equals 0. Okay, of course, this is the same thing as that one. It just depends on which approach you want to take. Do you go with the concept of going from high potential to low potential? Or do you go with the concept of, if I see a negative sign on my way, I'm going to assign a negative polarity, and if I see a positive sign on my way, I'm going to assign a positive polarity. All right, similarly for this circuit, if I follow the second procedure, second approach, I can say that, for example, if I start from here, right? This approach says, if you see a negative sign, then the voltage is negative. So I have a negative sign here. I'm going to write minus V2. Then I come down here. I see a positive sign. Then I say plus V3. I come down here. I see a negative sign, minus V4. And I go this way. I see a positive sign. I say plus V1 equals 0. Okay, and of course these two are the same. It's just multiplied by minus 1. So whichever approach you want to take is fine. You just take that and move along. Okay, so that's the definition of KVL that we have. And yet another approach is to write something like this. But that's not as easy as this to express. I'll just give you an example to show you a third approach that is handy in some cases. So, example. This is what we saw last time, and now it makes more sense in the context of KVL. So we have V1, or Vx, we called it, Vx, and then we have R1, we have R2, and this current is Ix. We have a series combination of two resistors. And we said, okay, well, Ix flows through R1, generating a voltage like so. We call this Ix R1. And similarly, Ix R2 across R2. So Ix R2. Okay? Now, I would like to write a KVL around this loop. How do I do that? Well, you can pick either approach. So, for example, let's say I go with approach 1. Approach 1 says that if you go down the potential, you write it as a negative value. Starting from here, I go down the potential, so I'm going to write minus Ix R1 for this voltage across R1, Ix R1. Then I'm going down the potential, so again minus Ix R2. And finally, I'm going up the potential from low to high. So that would be plus Vx equals 0. All right, so that's applying approach number 1. But a third approach, which is very useful in some cases, and if it's not that confusing, is the following. We can say, well, we have a voltage of Vx from here to here. So let's say 1 volt. And this voltage has to be equal to the sum of these two voltages, right? This plus this has to be equal to this. So I can write it as follows. So let's change the color of the pen. So I can say Vx, this voltage, is equal to, this voltage has its higher potential here, right? And these two have their higher potentials here. So I can say that that's equal to Ix R1 plus Ix R2. So this articulation that some voltage here is equal to the sum of some other voltages here is really KVL, except that it's worded differently, and it's very useful in many cases. So as we go along, we will see many examples of these things. We have seen that we can use Ohm's law and KVL and KCL to solve circuits. But interestingly, these laws have applications in some other places that we may not ever think about. One application is actually in the case for biology and for studying the blood pressure. So as you know, the heart generates blood with oxygen, oxygen-rich blood, and that blood flows through the arteries, and it is distributed across our body in different vessels or capillaries. And as it propagates through these vessels, it loses the oxygen, and then the blood that has lost oxygen comes back to the heart through these veins, and then this cycle continues. So of great interest to biologists and doctors is how much pressure we have in these different vessels. So blood pressure, of course, is extremely critical for many different situations. So in this paper, they say we can compute the blood pressure in these different veins and different vessels based on simple application of KVL, KCL, and Ohm's law. So for example, they say in this paper here, they say we modeled, for example, two vessels that are in series by resistors, or these branching effects. So for example, here you see that we have a vessel, then it branches out, and so on. So all of these can be modeled by resistors. And then they can also have switches to represent some of the action that happens in the body. And eventually, they arrive at these simple models of the vessels and resistors. And they say the blood pressure from here to here is equivalent to a voltage difference between here and here. And based on that, we can calculate all the currents and pressures, so to speak, and so on. So in fact, what they do is they say, for example, we may have a main vessel, which might call that a root vessel, and then that branches out into narrower vessels. So we model this by a resistor whose value is small, and then some other resistors whose values are larger. And then again, we have a voltage difference here, or some blood pressure here, and from that we can simplify and we can analyze. And they write simple current equations for how much blood flows through each of these vessels. So we see that these equations that we are learning actually have many other applications besides just solving basic circuits. Isn't that beautiful? All right, so that is KVL. Let's go and look at some examples. Let's see here. Let's go to the next page. Okay, so we're going to look at another example here. In this example, we have something like this. So we have a battery on this side called V1, a resistor called R1, a battery on this side called V2. And we would like to find this current, call it Ix. Okay? So it's pretty simple. We would like to find Ix in terms of R1, V1, and V2. So that's our quiz of the day. I will give you 60 seconds to think about it. did you get? Well, what we can do is the following. We say if Ix flows through R1, it generates a voltage across R1 according to Ohm's law. And that voltage would have to be denoted like this way. Ix times R1. How do I know to put the positive here and negative here? Well, remember that when we drew a resistor for Ohm's law this way, we said that the current is flowing from high potential to low potential, right? So that means that my voltage was designated like this, high potential to low potential. Now we can go the other way. We can say that if the current goes from this side to this side, the voltage designation has to be such that the current enters the higher side. The current enters the higher side and leaves from the lower side. So it leaves from this side. So that would be IXR1. So now I have three voltages, V1 on the left, IXR1 across, and V2 on the right. And I have a loop, so I can write a KVL. So let's write a KVL. Which approach should we take? We can take the first approach. We can start from here, and we say we're going up the potential, so this will be plus V1. Then we're going down the potential, so minus IXR1. And then we're going down the potential, minus V2 equals 0. Right? Or if you want to be adventurous, you can say this voltage is equal to this voltage plus this voltage, right? But anyway, so I'm interested in Ix, so I'm going to write Ix is equal to V1 minus V2 over R1. Okay, so I want you to remember this result, and we will explain or articulate this result as follows. We will say if we have a resistor of value R1 and the voltage on the left side is V1 and the voltage on the right side is V2, then the current flowing from the left side to the right side is given by V1 minus V2 over the resistor. I repeat, we're going to use this a lot later, so you really have to remember this, okay? So the voltage on the left minus the voltage on the right divided by the resistor gives us the current flowing from the left to the right. That's what we have to remember. Okay, very good. Let's go on to another example here and see what we can do. So this time we'll be a little more adventurous and try some other circuit. So in this case, we'll throw in a dependent source. So suppose I have a voltage here called V1. I have a resistor here, R1. And then I happen to have a dependent voltage source whose value, this voltage source is called V2, and its value is K times V1. Okay? All right. And my objective is to find this current Ix. All right? So the resistor is known. V1 is a constant voltage like a battery. And this V2 just copies this voltage and multiplies it by K. K can be any number we want. So we would like to see how much Ix is. All right, not a problem. So again, we follow the same procedure. We say this current flowing through this resistor will give us a voltage, and that voltage will have its higher end here and lower end here, and its value is Ix times R1, just like before. And now we go ahead and write our KVL. So starting from here, I say going up the potential is plus V1. Going down the potential from high to low, that's minus Ix R1. And then going down the potential from high to low is minus KV1 is equal to 0. So we're interested in Ix, so we can say that Ix is equal to V1 minus KV1 over R1. or if you want to simplify it, y minus k v1 over r1. Okay, so a nice little circuit that does this. One interesting point is if k is equal to 1, ix goes to 0. Why is that? Well, because if k equals to 1, this voltage is exactly equal to this voltage. So there's no voltage difference across the resistor, so there's no current through the resistor, according to Ohm's law. All right, very good. Let's go and look at another example. Well, we have a little more complexity in the circuit. So here's another example. So we start out with a current source, which we call I1. Let's see here. Okay, actually, no, that's not what I want to do. So let's start with the voltage source, which we call Vx. And this voltage source now goes through a resistor R1. Then we have a current source, which we call I sub x. And then we have two more resistors, R2, R3. And finally, we have one more current source, which we will call I sub y. Okay, so we have a bunch of devices connected to each other. Go ahead and draw the circuit for yourself. Okay, and we would like to write just some KCLs on the circuit to see what they look like. So let's try to write a KCL here. Now, the exact analysis of the circuit is something that we will look at a little later when we introduce node analysis. But for now, we're just trying to write some equations. We're not trying to solve the entire circuit yet. Okay, well, so let's call, for example, this current I1 and this current I2. I1 and I2 are not known. What we know are these quantities, right? These quantities, but we don't know I1 and I2. Eventually, we hope to find them. Okay, I can write the KCL here, right? Well, how would I write that? I would say this current is coming in, this current is leaving, and this current is coming in. So let's add up the currents that are coming in and equate the result to the current that is going out. So I can say that I1 plus Ix is equal to I2. Is that okay? So we wrote the KCL at this node. We can call this node something. Let's call it node A maybe. And KCL at node A gave us that result. All right. How about this node here? What can I say here? So this is node B. All right, so what I see is that I2 is coming into B, travels this way. IY is going out of B. And how about this guy? Well, we don't know his current yet, right? So we have to call this something as well. So we're going to call this I3, maybe this way. So a KCL at this node will look like this. I2 is coming in. These two are going out. So I2 is equal to I3 plus IY. Okay? All right, so these are two KCLs that I managed to write for the circuit. Can I write any KVLs? Probably. Let's try some. And again, we're just playing, right? We're just playing. So can I write some KVLs? Well, yes, why not? Let's change the color. How much is the voltage drop across R1? I have a current. The current flowing through R1 gives me a voltage. So that would be I1 R1, right? Just like before. Okay, and I have another voltage here, plus I2 R2. and negative on this side. How about this one? I3 flows through R3. So I3 is going from high potential to low potential, right? From here to here. So the voltage has to be positive up here, negative down here, and its value should be I3, R3. So now I can write a KVL. The KVL starts from here, travels through this, travels through this, travels through this, and comes back to the same point. These are all connected by a piece of wire, so they consider the same point, the same node in the circuit. So I can say Vx, so going up the potential plus Vx minus this voltage, I1 R1, minus this voltage, minus I2 R2, because we're going down the potential, going down the potential, going down the potential, minus I3 R3 equals 0. Do these three equations allow us to solve the circuit? Yes. We have three unknowns, I1, I2, and I3. We have three independent equations, these two and this. So if we solve all of these, we can find the three currents, and from those three currents, we can find anything else that we want. All right? So at this point, you might be wondering, this seems rather random. How did I pick these currents, and how did I write all of this, right? But we will see a little later that we have a methodical approach to writing these equations, so that we don't have to hunt for equations, we don't have to worry which equations are dependent and which equations are independent. So that would be the subject of node analysis and mesh analysis that we will look at later. All right, this completes our lecture today. I will see you next time.